So next up, as far as derivative shortcuts are concerned, we are going to talk about what is known as the product rule. The product rule is going to be used anytime you have a product of two functions of x. So if you had something like a polynomial that was in its factored form, you could use something like the product rule to help you out. Now, one big intuitive thing that you might think when you see this is, based off of how the sum rule, the difference rule, and whatnot went, wouldn't it make sense if it was just take a couple derivatives and be done? What I'd like to do is test this theory. I would like to consider two functions. One of them is y equals x to the fifth power, and one of them is y equals x cubed times x squared.
Spoiler alert, guys, they're the same function.
If I were to apply the power rule to take a derivative in the first case, that would give me 5 times x raised to the fourth power. If I were to attempt to use the power rule on both of these things over here, that would be 3x squared times 2x. And if I multiply those together, I get 6x cubed. This is the correct derivative. This is not. Which lets us know that this guy right up here is absolutely not true. Now, the derivation of where the product rule comes from is not nearly as important as the result, but because I'm a mathematician, I gotta do it. So suppose that we have y is equal to f of x times g of x. This means that the derivative would be equal to the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. If we were to attempt to use the direct substitution property with this, we would wind up with 0 divided by 0, and that is really not helpful to us. So just like we've done for a lot of our derivative shortcuts, what we're going to do is manipulate this using algebra to see if we can make something good happen. The algebraic manipulation that I'm going to do is an algebraic technique referred to as adding 0. What I'm actually going to be doing is adding something and subtracting the same thing to get this into a different form where it's going to work out better. So the first term, sorry, that should be f of x plus h. We'll just retry that. F of x plus h times g of x plus h. Then we're going to subtract something. Then we're going to add the exact same thing. And then we're going to have a minus f of x times g of x down at the end. The thing that I'm going to be adding and subtracting, or rather subtracting then adding, is f of x plus h times g of x. F of x plus h times g of x. Now, the answer to the question, why did I do that? The short answer is because it works, and I'm going to demonstrate how. What I'm going to do first is split this into two fractions at this plus sign right here. So I'm going to take this big fraction plus this big fraction. You'll notice that with these first two terms, though, they have a factor in common. The factor in common that they have is f of x plus h. So we're going to call this the limit as h goes to 0 of. I'm going to factor out that f of x plus h, and I'm going to copy down everything else that's there. Well, that would be g of x plus h from the first term minus g of x from the second term all over h. I'm going to do the exact same thing, but I'm going to do it with the last two terms up here. So the observation to make is that they have a g of x in common. And if I factor out that g of x, I'll be left with f of x plus h minus f of x all over h. You'll notice that after I factored out those common factors, this is now a difference quotient. It's the difference quotient of g. This is now a difference quotient. It's the difference quotient of f. Therefore, as I allow h to go to 0, we'll say that's the direct substitution property, though it isn't really, this will become the derivative of g. This will become the derivative of f. this will become f of x because h is going to go to 0. So that is f of x times g prime of x plus g of x times f prime of x. So when you start with the product of two functions, the product rule states that the result will be the first function times the derivative of the second function plus the second function times the derivative of the first function. Both of these will contain an f and a g, and each one of them will be differentiated. A different one will be differentiated in each of these. Now, just to make sure that it works, I want to retry what we did earlier. We differentiated x cubed times x squared, and we wound up with a wrong answer doing the wrong method. So now let's try the correct method. So this will be the first function times the derivative of the second function. Second function in this case would be x squared. That becomes 2x. Plus the second function, which is x squared, times the derivative of the first function. First function is x cubed. That derivative would be 3x squared. It's all algebra all the time from here. This is 2x to the fourth plus 3x to the fourth, giving us a total of 5x to the fourth, which is, in fact, the correct derivative of x raised to the fifth power. So there is quite a bit of credibility to what we just did. More examples to come.